So it's finally time to actually solve these models. We've previously specified everything through the global definitions, through the different components. Now we're arriving at the larger scale node, which are the studies. So the studies are where we start to look at what we're actually wanting to do with this thing. Do we want to look at the steady state after a certain amount of time? Do we want to watch it progress towards a certain amount of time over, say, 10 minutes or an hour or something? Do we want to do a steady state and then add a transient where something changes? All of a sudden you introduce a heat source and then watch how it changes up to, I don't know, a certain amount of time, and then you do another steady state. All of this is possible by ordering things. So when you down click on this chevron, what you're going to see are a series of steps. In this particular case, it's only going to be step number one, which is a stationary solve. As the name implies, this is a stationary solution, so we're looking at the steady state. In later videos, we're going to explore being able to layer these or construct different studies. So in one case, maybe we want to do stationary, then transient. In another one, we want to do stationary, transient, then eigenfunction analysis. Or any of these other things are all possible by moving these things around. When you actually click on one of these steps, what you're going to see is a few different options. It's fairly advanced, this sort of thing. So I'm not going to go into a great deal of depth now. Rather, I'm going to show you the broad strokes of what's happening. And then in later examples, when we're looking at particular tutorials, that's when we'll dive into it so that you have a bit more of context of what's going on. Okay. So the important things here are what physics is actually being solved. Again, for multiphysics, this can be nice because maybe you only solve one physics at a time. Let's solve the fluid flow first and then add temperature, then add electromagnetics, and that way it's a bit more computationally tractable. I'm going to skip past all these, but we will return to it at one point. Solver configuration is where you point to the step and then you tell it how you want it to actually solve for that. We're going to come back to these in later videos with particular examples. I just want to show you, though, that there is this stationary solver. So later on in 3NM4 numerical methods, we're going to talk about how these things are actually being solved. But thankfully, lucky for you, at this point, you don't need to worry about that right now. So the big key here is confirming, yes, we're using step number one. Relative tolerance, because we're looking at an approximation, we're going to make it as good as we can. How do we say as good as we can? Well, we specify a tolerance and say when this tolerance is met, then we're good. Linearity, yes, you can change between nonlinear, linear perturbation. It will save you a little bit of time on the computation, not really significantly though, to be honest. So I would stick with automatic here. Output, don't worry about. Results while solving is actually very useful, but I'll save that. Let's see, the log is actually what's over here too. And that's it for this guy. When we look into the more advanced settings, it gets complicated quickly. Let's skip past this one. Fully coupled, we're going to come back to in the context of segregated versus monolithic solves. Don't have to worry about that right now. But this is where you get into more of the numerical methods. If anybody remembers Newton's method for root finding, here's Newton. Right? There are other techniques. There's a constant Newton. There's the adaptive. There's highly nonlinear, which is a change in settings. Double dogleg. There are different techniques for it. And then you get to the actual linear system solver, which is the workhorse of the finite element method. Here you get to specify this, and hallelujah for you guys that this is all pre-done and pre-built and even selected good defaults for it before you even start down this. There are other objects. Algebraic, multigrid, AMG, I'm not sure if we're going to get to, or geometric, or basically anything past the segregated solves. Then what you have to do, so now you specified how you want to solve it, you can click, now you actually have to do it. Okay, so what you want to do is click either compute here, or you right click on the node and you hit compute, or there's even a nice hotkey for you here. And if you watch down here, you're going to see your progress bar. As it moves across, this particular case has very few degrees of freedom. I think it's something on the order of 700. So it solves very quickly. Once you get up to 10,000 or 100,000 or up to 1,000,000, that's when you have to be careful of your RAM, but we'll cross that bridge when we come to it. And this is your solution. You'll see that it's already by default jumped down to the results, which will be the next video.